Hello everyone. In today's video I want to talk about a very important stuff. So in the last video, which I have linked here, so you should find a link appearing in the corner, or I'll also mention it at the description. In the last video, where we talked about the physical concepts behind general relativity, we talked about the existence of a quantity which is called a spacetime. It's an entity where the magic happens. The particles follow their trajectories, and not only the space-time is just a background where things happen, but the space-time also itself is a player in the relativity concept. So we'll have to know what actually is a space-time. Now, if you ask a hardcore physicist who is true to the theoretical mathematical conviction, they will mention a bunch of stuff, like it's a four-dimensional topological manifold, it has some layers of structures, such as it has a connection, the connection is a special one which is torsion-free, it has a compatible pseudo-Riemannian metric, it has a time orientation, and so on and so forth, which I frankly have indicated on the thumbnail of this video. So if you notice at the thumbnail, some of those things are listed. And now I must confess the fact that if you really want to understand relativity at a deep fundamental mathematical level, you should at some point of your life go through these stuffs, and that take a lot of mathematical framework. And to reach up to the point where you can comfortably understand these topics, you'll have to spend a lot of time. Now, I'm not saying don't follow those, because understanding those topics are crucial, and we will eventually cover a lot of those topics as we go along, because they are essential in understanding the relativity, and it truly worth spending the time. But my goal is to quickly dive into the essential stuffs. So, for example, in a situation, you probably are taking the relativity course for the first time, or being exposed to this subject for the first time altogether. I think it's a good idea to trim some of the fat which are conceptually nice, but not of immediate necessity. So by keeping that in mind, I shall talk about space-time in as simple terms as possible, but I will not deprive you what the necessary stuffs are, and I will not deprive you of the essential fun you need to have and you will have if you take the course of relativity. So without further ado, let us try to understand this concept of space-time. Now, when we start defining the space-time, these phrases might come up, right? So a lot of things will come up, and these particular words are going to precede everything else. Space-time is a four-dimensional, so this part is understandable, pretty much. Topological differentiable manifold. What does that mean? Why would we even need to understand that? Understand this, the general structure of physics is that it's a bunch of differential equations, some ODEs, some PDEs, some ordinary, some partial, mostly partial. It's a bunch of, let's say, partial differential equations trying to emulate the reality being the physics happening in nature. That's what we need, right? Now, typically, we define a bunch of structures, right? Topological structures, the space that we are talking about, where actually the physics happening, and so on and so forth. The mathematical objects that we are using, where are they? What kind of objects are they? We have to specify a lot of things, right? But in a sense, we have to do calculus. We have to solve differential equations. So a manifold is essentially a space where we can perform calculus. That means we can differentiate functions and we can integrate functions. or integrate objects that are very specific kind of functions. We shall talk about them later, something called forms. But nonetheless, this is in a sense what a manifold is supposed to be. Now, what we are accustomed to do is to perform calculus or multivariable calculus on what we call a flat Euclidean space. In mathematical terms, we call them Rn. Okay? So that's a flat familiar space that we can do calculus on. But also, you can do calculus on curved space as well, right? For example, on spheres, on torus, on cylinders, on higher dimensional complicated structures. So all of these structures have one thing in common, is that if you zoom in, right, in other words, local to a point, that means in the vicinity of a point, they looks like those initial flat Euclidean spaces. So intuitively, we define manifolds. Manifolds are spaces that looks like Rn locally. Why Rn? Because Rn are rich in structures. We can do calculus on them. They have a natural vector space structure. They have very nice metric structures, and so on and so forth. So if your space locally looks like Rn, yes, you can do calculus on it. So what are the advantages of having a topological differential manifold? One of the great advantages is that you can draw coordinates on them. All right. Now, coordinates are what we call homeomorphic maps to Rn. What essentially that means is that you can draw what happens in the real world. It doesn't have to be a real world, by the way. So, for example, your world can be this sphere where a particle is moving along a smooth curve-like shape or structure, but just a curve, and then you should be able to understand that or analyze that without losing information in a coordinate system where calculations are immensely easier. And in fact, we only know to do calculations easily if we have a coordinate system, but like the physics is happening on the sphere, not in the coordinate. So what you need to do is to translate that analysis back into your original space and find out what is going on that space. Understood? So we have to, well, probably, we have to use the coordinate only for the benefit of the calculation, but the real physics is always happening on the original space. So we have to go back. So this act of going forward and backward information and analyzing them without losing essential information is what is being guaranteed by the homeomorphic coordinate map. Understood? So that is the advantage of acting on a manifold. But now, since the coordinate is a construction of yours, right? It's your mental image. It might happen that different observers or different people might use different set of coordinates, right? So let me draw that into a picture. So, for example, here's a space or a manifold, right? A differentiable manifold with a topology M. There is a hole in it and different stuff, and there is a particle moving on it like this. All right. So you want to understand the motion of this particle. So what do? You want to set up a coordinate around the place where motion is happening. So let us choose a point on the trajectory of the particle, and let us call this point P. All right. So now you want two of your friends to analyze this motion. So what happens is that one of your friend is red, so he comes up and he chooses what we call an open set or an open area in the vicinity of this point. That also includes this point. But he cannot cover the whole of the manifold with his coordinate system. Why? Because in general, objects or manifolds do not have global coordinate systems, right? That means you cannot have a coordinate that covers the whole area. When you want to do that, you quickly run into mathematical difficulties. So what he does, he chooses a patch or an open set and tries to establish a coordinate system locally, right? Because remember, GR is a local theory, and for now, just knowing about the vicinity of the trajectory and the motion would suffice. So your friend named Red comes up, and he establishes a coordinate system, which we call the red coordinate. And so he chooses this area here. Okay, so, and in an effort to translate that in a homeomorphic relation with his established coordinate system, he takes this image, which replicates the chosen open set on the manifold. All right, so he calls his coordinates as x, so you have x1, x2, x3, all the way to whatever the dimension of M is. The coordinate will also have the same dimension, and he has the image of this point, which is denoted by x of p. All right, but remember, you invited two of your friends. One is red and the other one is blue, and blue comes up with her own coordinate system, which she calls the y coordinate, right? And she chooses an open set like this that incorporates the point P, and it has an area of intersection or an overlap with the area that red chosen in his coordinate system. And in the coordinate system of blue, we have a representation of the point as well. So that point has the coordinate y of p, and using the blue line in the red's domain and the red line in the blue's chosen domain, we have denoted the point of intersection. Okay? And in order to properly preserve the physics, what we would require for these two coordinate systems to respect is that they must be compatible with each other, so that we may easily go from one coordinate of convenience to another coordinate of convenience, while in the meantime keeping the physics unchanged. Now, is it always possible that we don't mess up with the physics, even though we choose the coordinates with utmost carefulness? The answer is yes, we will mess up despite our best try. But there is the cleverness. If you mess up in one coordinate system, or if your coordinate system has some limitation, if you have this compatibility in a given region, in the region of the intersection, then you can go from one coordinate system to another where you don't have that particular issue. And this is what's so great about the compatibility of coordinates. Now, in your book of maps, right, which mimics the world, right, even though the physics is happening in the world, the maps are just replicating the image of the world in your book. In your book of maps, you must keep all the compatible maps together. Similarly, if we collect all the compatible coordinates, then that gives us what we call an atlas. All right? An atlas is the collection of all the compatible coordinates that covers the manifold. All right? Now, if you collect all such covering coordinate atlases, that gives you what we call the maximum atlas. And the name is, as you may surmise, literally is taken from the concept of atlas, because that's essentially what we are doing when we are setting up the coordinates. We are basically drawing maps in such a way that preserve all the relevant information required to navigate this world.
Now, this is all nice and dandy, but this is not enough. Why not? Because remember, if we want to talk about the physics on the manifold or the geometry, we need other stuffs as well. So, for example, how to measure the volume, right? Questions like that. But more importantly, how to measure the distance. And the coordinate system instinctively or inherently does not give you any prescription for that, because the distance is independent of any coordinate, the distance between 2 points actually. And mathematically, if you look at the concept of distance, which we also call the metric, you'll notice it's possible to define different kind of metric on a manifold. But here we're lucky because of special relativity. We know that in a flat spacetime, we have a prescribed spacetime metric, which is essentially the formula for finding the distance. So for example, in Euclidean space, you had the formula for differential distance, which was given by ds squared, which is, for example, dx squared plus dy squared, let's say, on a Cartesian coordinate on a two-dimensional flat Euclidean space, or perhaps we had it in different coordinate as well. So for example, we could have written it in polar coordinate d rho square plus rho squared d phi squared. In the Minkowski spacetime, we are introduced with the metric ds squared equals, because it's a four-dimensional spacetime, we now have time, so dt squared plus the special part, so for example dx squared plus dy squared plus dz squared, like that. Or for example, if we have a cylindrical polar coordinate system for the special part, then the same metric would be found by this formula here, right? And you can go on to any coordinate system you want. Just as a record, I shall mostly stick to the Cartesian expression for distance whenever I can, but that is of course going to change frequently because we always have to change our coordinates. So this is true for a flat space. In general, a coordinate system can have different coefficients than the coefficients we have in the flat metrics. For example, here, or for example, let's say I'm talking about the Cartesian coordinate system as well. So there would be some factors in front of these coordinate systems, or this coordinate differential squared. So something into dx squared, something into dt squared, and so on and so forth. And so that will be, in general, the case for curved manifold. But you have to be careful here. Why? Because if you have an expression, a coordinate expression for the distance or for the metric, that doesn't automatically mean it's a curved space. All right? So keep that in mind. From the expression of the coordinate, or the coordinate expression of the metric, you cannot find out a priori whether the space is curved or not. In order to understand a curved space, you need other mechanisms which can extract information from this stuff, from a metric or a distance, and then it can calculate by hand to tell you whether or not that space is curved. Understood? I have seen many pop science books that have frequently got this wrong. I've seen people who claim they understand relativity and they can somehow magically, by just looking at a metric, which, by the way, can be easily seen to be a flat metric just written in a band coordinate system, to be curved metric, or the metric of curved space, which sometimes can be absolutely nonsense and annoying and can lead to faulty results. So as a student of general relativity, you must remember this thing. The metric or the concept of distance is essential in general relativity, but from this expression alone, you cannot possibly tell, well, unless you have tested that in different occasions. But just by looking at a random metric, you cannot tell whether or not that space is curved. Or, for example, what kind of curvature is there? So in physics, we are mostly and physically interested in a special kind of curvature, which is called the Einstein curvature tensor. Okay, that's the most important part. And the Einstein curvature tensor is written by a capital G, whose expression I hope to show you in future. And why is this important? Because this is the essential part in writing the Einstein field equations, where this G governs the, I shouldn't say govern, this G measures the special kind of curvature which is linked to the source, which is written as T here, or which is governed by the source, and they in turn have impact on each other. And this is, the source is written by T, which in details called the stress energy momentum tensor, which is a big name, by the way. In short, it's almost always called the stress tensor or stress energy tensor. Okay, and the equation that's been written here is called Einstein's equation, and space-time follows this Einstein equation. Okay, so in this video I have mentioned three things. One is that space-time is a four-dimensional differential manifold, right? It has a special kind of metric. Notice that all the metrics I've written for the spaces have all positive signs, but the metric describing the flat space here, or any general space-time here, flat space-time or general space-time, has this special negative sign, which makes it different than just spatial metric, or metrics for that matter. This is called the Lorentz signature or Lorentzian metric, also called pseudo-Riemannian metric. So these are big names. I'll repeat them over and over again so that as you go along with this series, you will remember these names and be familiarized with these concepts. But, oh, by the way, I have also mentioned that the space-time actually satisfies the Einstein field equations. The reason I'm calling it equations in plural, because it's not just one equation, all right? It's a bunch of equations clamped together in a special mathematical consistent structure, and it has, truth be told, it has 16 equations packed together. That's why it's called the Einstein field equations. So that is, in short, the description of space-time. In future videos, I shall show you other structures that space-time possess as well. If you look at a deeply reached mathematical book, mathematical physics book, by the way, you'll have more things to explore. But in short, this is the simple description of space-time. Until the next time, thank you very much for watching.